So now let's talk about the orthogonal complement of a subspace. So the orthogonal complement. Um, so I think the best way to kind of visualize this is with an example. So this is going to be some statement that's going to be kind of nicely abstract and generalizable, but I want to start with an example. So what I want to do is I want to take, let's take two vectors. Let's say v1 and v2 are two vectors in R3. So v1 will be the vector 1, 2, 0. v2 is the vector 0, 1, 1. These vectors are not linear multiples of each other, so they're linearly independent. Okay, and what I want to do is I want to think about the subspace that you get by spanning these two vectors. Let's call that W. And so the span of these two vectors is going to be exactly the set of vectors or the set of matrices A, comma, 2A plus B, comma, B, where A and B are in the real numbers. They're elements of the reals. And so that's going to be the subspace W spanned by the two vectors. And what I want to do is I want to compute what I'm going to call W perp, which is the orthogonal complement. So this is the orthogonal complement of W. And what I want to do is I want to calculate all of the vectors in R3 where W is orthogonal to, I shouldn't use W, let me use X, just so that there's no confusion here. But this is going to be the set of vectors X in R3 where X is orthogonal to every vector in W. Okay, so take any vector like this. I want to think about what does it mean to be orthogonal to that vector. And so if you kind of think about what that means, you can kind of do this in general, or a nice kind of trick is that if you know the basis for the subspace, you can just check that your vectors are going to be orthogonal to v1 and v2. So yeah, we'll just do it that way. So I'm going to take x, y, z. So I want to find all the vectors like this. Let me make this an x vector so that that's different than the real number x. And I want to take and find all the values, all the real numbers, x, y, z, where the dot product of x and y and z are orthogonal to 1, 2, 0 and 0, 1, 1. And if I do this, what ends up happening is I get, let's see, for the first dot product, that's x plus 2y. And if they're going to be orthogonal, I want the dot product to be 0. And likewise, for the last one, we get y plus z being 0. And so all of the values x, y, z that follow this pattern are going to be in this orthogonal complement. And so it turns out that a nice way to do this is if I want to talk about the solution set, I can just parameterize by letting y be t, and then x will be negative 2t, and z will be negative t. And so W perp is just going to be all of the vectors that are negative 2t, t, and negative t, where t is a real number. So that turns out to be the orthogonal complement of W. And this should feel, there's a reason why we're talking about all this in a linear algebra class, of course, but this should feel very, very much like looking at the null space and row space, and for good reason. It turns out that if I take the matrix A formed by the two vectors, so let's let A be the vector, or the matrix rather, 1, 2, 0, 0, 1, 1. So the top row is the vector v1, the second row is the vector v2. And if I want to look at the null space of A, that's exactly what we just did. It turns out that the null space of A is exactly W perp. It is all the values. How do I want to write it? It's all the values where, let's just do it this way. This is going to be the span of, let's just do it that way. This is the span of negative 2, 1, 1. Okay, I'm not writing this very well, but it's the span of that, that vector. Okay, so if you take -2, 1, -1, that's the basis vector for the orthogonal complement, and you get that from looking at the null space. So the orthogonal complement and the null space are kind of tied together. They're very similar ideas. In fact, they're identical. When I say they're very similar, what I mean is they're the same. So that's what the orthogonal complement is. So you can just kind of in general, we'll talk about this connection with matrices at a later date. So now that we have a connection to this orthogonal complement, in order to describe the null space, remember that we have in the what I call the equivalency theorem, one of the things that we can add to it, we already know that the determinant being 0 and the null space being what it is are tied together. So if the null space is just the 0 vector, then the determinant of our matrix is non-zero. And likewise, since the null space and the orthogonal complement are the same, we can add this orthogonal complement to the equivalency theorem. So that whole long list of things that are all equivalent, we can add the orthogonal complement in. So we might do that at some point. In general, it turns out, and I might as well just say this, if A is an n by n matrix, so if A is an n by n matrix, then my iPad's running away again, then the determinant of A is going to be non-zero if and only if the orthogonal complement of the row space is just the 0 vector. That's basically what I just said before. So anyways, so we know that the determinant is non-zero if and only if the null space is just the 0 vector. The orthogonal complement is the null space in a certain sense. So anyways, we can tie all that nicely together if we want to. So I think that's everything that I wanted to say about the orthogonal complement. So in our next video, we'll talk about how to generalize this idea of dot products.